Welcome to Brain Vision.
In the first part, we want to find the electric potential at point P, which is at a distance of x from the right end of the rod. So here, first we will divide the rod into infinitesimal portions. So here we will consider an infinitesimal portion, that is having length of dr and having charge on this portion is dq, and this small portion is at a distance of r from the right end of the rod, and the value of this r goes from 0 to a when we move from right to the left of this rod. Now first we will write the relation for electric potential due to this small portion at point P. So we have dVp is equal to 1 upon 4 pi epsilon naught, the charge on this small portion divided by the distance of this small portion from point P, which is x plus r. As we are given in the problem that the charge is distributed uniformly on the rod, so we can find the charge on this small portion by using the relation dq equal to the charge per unit length, that is total charge divided by total length of rod into length of this portion, which is dr. So by putting the value of dq, we will get the potential at point P due to this small portion equal to 1 upon 4 pi epsilon naught into q dr divided by a whole divided by x plus r. By rearranging, we can write this as electric potential due to this small portion at point P equal to 1 upon 4 pi epsilon naught times a into q dr upon x plus r. So this is the electric potential at point P due to a small portion on the rod. Now we can find the total electric potential due to this rod at point P by integrating this relation, that is electric potential at P due to the rod equal to integration of dVp from 0 to a. This gives us integration from 0 to a 1 upon 4 pi epsilon naught a q dr divided by x plus r. By writing the constant terms in front of integral sign, we will have Vp equal to, here charge on the rod is constant, so q upon 4 pi epsilon naught, and length of rod is also constant, into integral from 0 to a 1 upon x plus r dr. Now by using the relation integral from integral of dx divided by ax plus b, which is equal to 1 upon a log of ax plus b, we can write the integral as vp equal to q divided by 4 pi epsilon naught times a ln of x plus r. Here the coefficient of x is 1 and here limits are from 0 to a. We can put the limits here q upon 4 pi epsilon naught a into ln of a plus r ln of sorry ln of x plus a. Here we are integrating with respect to r, so we will put the value of r here minus ln of x plus 0. By using the formulas for logarithm, we can write q upon 4 pi epsilon naught times a ln of x plus a divided by x. So this is the electric potential due to this rod at point P. Now in the B part of this problem, again we have the rod. The length of this rod is A, and we want to find the electric potential at point P, which is directly above the right end of the rod, and this point is named as R. Let this point is at a distance y from the end. Here again we will assume a small portion on the rod at a distance of r from the right end. Let the length of the small portion is dr and it has a charge of dq. Now the distance of this small portion from point r can be calculated by using Pythagoras theorem, and that will be equal to r squared plus x squared whole to the power half. Again we can write here the contribution of electric potential due to this small portion, which is dVr is equal to 1 upon 4 pi epsilon naught times the charge on the small portion divided by the distance of small portion from point r, which is y squared, which is r squared plus y squared. Sorry, I did a little mistake here in the diagram. Here the distance of the small portion from point r is r squared plus y squared. Again we can write the charge on the small portion equal to the total charge on the rod divided by length of the rod, that is the charge density, which is defined as charge per unit length into length of the small portion. So we have the contribution of electric potential due to the small portion at point R equal to 1 upon 4 pi epsilon naught, and we have dq equal to q dr divided by a upon r squared plus y squared. By rearranging, we can write this as dvr is equal to 1 upon 4 pi epsilon naught times a q dr divided by r squared plus y squared. Now the total electric potential due to this rod can be computed by integrating the above value, that is electric potential due to rod at point R is equal to integration of dVr from 0 to a, and we have dVr equal to 1 upon 4 pi epsilon naught a q dr divided by square root of r squared plus y squared. We can write Vr as q divided by 4 pi epsilon naught a, and integration from 0 to a 1 upon y squared plus r squared whole half into dr. By using mathematics, we can write Vr equal to q divided by 4 pi epsilon naught times a, and the integration of 1 divided by square root of y squared plus r squared, that is equal to log of square root of y squared plus r squared ln of square root of y squared plus r squared plus r, and here we have limits from 0 to a. Here we have used the integral, that is 1 upon square root of a square plus x square dx is equal to log of x plus a square plus x square. Now here we will put the limits. First we will put r equal to a, then we will put r equal to 0. So this gives us electric potential at point R is equal to Q divided by 4 pi epsilon naught A, and we have ln of ln of y square plus a square plus a minus ln of y square plus 0 plus 0. This gives us Vr is equal to Q divided by 4 pi epsilon naught times A, and here we have ln of y square plus a square whole square root plus a minus ln of y. Now we can write this as VR, that is electric potential at point R, is equal to Q divided by 4 pi epsilon naught A, and by using the formulas for logarithm we can write this as y square plus a square plus a divided by y. So this is the relation for electric potential at point A due to this rod. Now in the next part of this problem, here we will assume that the distance x, that is the distance of point P from the rod, is very greater than as compared to the length of rod. As we have already calculated in part A of this problem, that electric potential due to rod at point P is equal to Q upon 4 pi epsilon naught A log of x plus A divided by x. We can write this as Q upon 4 pi epsilon naught times A log of 1 plus A upon x. Now by using the expansion of 1 plus x, that is equal to 1 plus u, that is equal to u minus u square divided by 2, and the next higher order terms. By using this expansion we can write this as potential at point P equal to Q divided by 4 pi epsilon naught A into expansion of log, here is u, here u is A upon x. So we can write A upon x minus half into A upon x square, and we have next terms of A upon x whole cube, then we will have A upon x to the power 4, neglecting all these higher order terms. As we have already mentioned that x is very greater than a, therefore we will have A upon x whole square is approximately equal to 0. This gives us potential at point P equal to Q upon 4 pi epsilon naught A upon x minus 0. So we will have potential at point P equal to Q upon 4 pi epsilon naught into x. So when x is very greater than as compared to the length of rod, then the rod will act as a point charge. Again, when the point R is very far from the rod, that is when y is very greater than the length of rod, then we can write the potential at R, that is equal to q upon 4 pi epsilon naught a log of square root of y square plus a square plus a divided by y, as y is very greater than a. Here we will equate a square, that is approximately equal to 0. This gives us V r equal to q upon 4 pi epsilon naught a log of y plus a divided by y, and this is similar to the relation which we found for part A. Now we can write the potential at point R equal to q divided by 4 pi epsilon naught a into log of 1 plus a upon y. Again, by using the expansion of ln of 1 plus a upon y, we can write Vr equal to q upon 4 pi epsilon naught a, and we will get the expansion equal to a divided by y. So far y very greater than a, we will have expansion of ln of 1 plus a upon y equal to a upon y. So here a and a will be cancelled, so we will have potential at point r equal to q upon 4 pi epsilon naught into y. So this is the same relation as electric potential of a point charge. So here we will conclude that when the distance of point r, that is y, very greater than the length of the rod, then the rod will act as a point charge.